Thank you. So I'm going to talk about our paper, Complex Dynamics and Autobidding Systems. Given kind of the limited time, I'm really just going to walk through how do you build or what's the recipe for cooking up complex dynamics in autobidding systems. This is joint work with Renato, Georgios, John, Song. Let's see, John, Song, Renato might be in the audience, so the authors are here. And we're all from various parts of Google. Let's see if this works with the PDF. Oh, it does. Okay. Well, if you were in the one of the really nice workshops yesterday, you heard a lot about autobidding, but if you weren't, let me recap. So by now, autobidding is actually the majority of online advertising spend. For some estimates, accounting for more than 80% of spend. So it's really important, critical to understand the behavior of these auto bidding systems, the long-term behavior as well as the day-to-day behavior. So there's a lot of money at stake in terms of these auto bidding systems. How should we think about auto bidding systems? Auto bidders participate in an auction. So of course we can use economic theory, auction theory. Traditionally, that means an analysis of the equilibria. Different aspects of the equilibria. But when we think about auto bidders, what are auto bidders? Well, they're automated agents that are interacting with each other thousands of times, potentially per second, in a repeated fashion. So over and over again. So another way to think about them is that these auto bidders actually form an ecosystem. We can study that ecosystem in terms of biology. Biology, of course, studies everything from normal ecosystems all the way down to genetic networks. Instead of focusing on equilibria, biology often thinks about long-term behaviors in terms of oscillations and things that are more complicated than oscillations. So oscillations are fundamental, really. Circadian rhythm controls when you wake up, when you go to sleep. Different aspects of predator and prey also leads to their interactions linked to oscillations. Okay. So a few more kind of remarks about why it's so important to go beyond an analysis of equilibria. And here I'll be echoing remarks from Steve Smale. And Smale is a very prominent mathematician, won the Fields Medal for his contributions in topology. He started looking at economics through the lens of kind of dynamics and topology back in the 70s. He has a very nice perspective in American Economic Review, where he makes some simple but pretty profound observations about equilibrium theory. And what he says is, okay, even if you go to all the trouble of showing that an equilibrium exists, let's say by the standard fixed point theorems, you haven't described how the system will get there. And in fact, you don't know if the system will get there at all. So in recent work, other work with Christos Papadimitriou, Georgios, and Jason, we actually showed that there can be games where no game dynamics will converge in an appropriate sense to the set of Nash equilibria. So this question of, even if you show equilibria exist, should you worry that the system will eventually get there? That's a fundamental question. So that really calls for looking beyond just the equilibrium in the system. And so kind of a lot of the ideas in the paper, we're going to be studying dynamics. And dynamical questions are what happens with the system for some particular initial condition? How does the behavior depend on initial conditions? Still kind of speaking to this slide. Are there multiple equilibria in the system? Are the equilibria stable? Are there more complex dynamics than just equilibria? Okay, so let's return to auto bidders. So again, if you were in the workshop yesterday, this will be very familiar. Let me cover it again. Auto bidders are basically proxy agents that bid on behalf of, let's say, advertisers. An advertiser submits some high-level information to the auto bidder. For this talk, it'll be a return on spend target. The auto bidder takes this information and uses it to construct bids. which it bids into this central auction and multiple item auction. And for the talk, it'll be a second price auction. Then the auction, of course, determines payments, allocations. Those get fed back into the auto bidder. The auto bidder uses that information to adjust the bids on behalf of the advertiser. So formally, the auto bidder is trying to maximize the value subject to a constraint. And the constraint being that the value is more than the return on spend target times the spend. And for kind of ease of analysis, we can just assume that this target is 1 by dividing appropriately through by the value. What's often done for these auto bidders is actually to adopt a strategy called uniform bidding, where the auto bidders just control a single multiplier and use this to construct the bid. So they construct the bid by applying the multiplier on top of the value. So the auto bidder just has to control this one scalar, really. Okay, so what's the automation part of the auto bidder? So again, there's just one number that the auto bidder is controlling. How should it adjust? Well, if we look at the constraint and we rewrite this, we see that it's really just the utility. And if your utility, and the auto bidder wants to keep the utility positive, that's the constraint. If the utility is negative, then the spend is too high relative to the value. You need to decrease your bid by decreasing your multiplier. So if the spend is too high, the utility is negative, you need to bring down your multipliers. On the other hand, if you have positive utility, value is more than the spend, there's slack in the constraint, you can increase your multiplier and increase your bid and you can get more. So you can set up a simple ODE really. The time derivative of the multiplier is just the utility. This will be the dynamics that we're working with. Okay, so let's see how this works for a very simple example. This will be a 2-bidder example, but it's a very nice example because it shows how rich the global dynamics can be actually in these systems. So there'll be 2 bidders, 2 items. One bidder has an item that it values highly. So bidder 1 has a higher value for item A or value for item B, and vice versa for bidder 2. Like, what would be a natural equilibrium in the system? Natural equilibrium, you might think, okay, what about the equilibrium where bidder 1 wins item A, bidder 2 wins item 2, or item B? So they're both winning the item that they value more highly, and they're what would that look like? So let's try just having the multipliers 2 and 2. So if you have multipliers both are 2, you under uniform bidding, you construct the bids by using the multipliers on top of the values. These bids get put into the auction. The auction is central second price. Auction determines the allocation of prices, second highest price. And then these prices inform the utilities. So what's the utility? That's just the value minus the payment. So both utilities actually vanish. So what does this mean? If the utilities are 0, then the right-hand side of that differential equation is 0. This is an equilibrium. Okay, so the multipliers remain constant. So there is an equilibrium here where bidder 1 wins item A, bidder 2 wins item B, both pay their value. Is this equilibrium stable or is it unstable? Okay, so it's a good question, and we can think about that, can explore that by kind of continuing in the example. So let's change the initial conditions here slightly. Let's imagine that the first multiplier started high, second multiplier started low. Bidder 1's multiplier is high, bidder 2's multiplier is low. What happens in that case? Well, that means that bidder 1 is able to put a lot of pricing pressure on bidder 2. Bidder 2 can't put much pricing pressure on bidder 1. So bidder 1's utility is positive, bidder 2's utility is negative. That means that the differential equation basically says M1 is going to increase, M2 is going to decrease. And
Sorry, the return to spend is not great in this equilibrium, right?
The
Return on spend, the ROS is not great in this equilibrium. So is that requirement, that constraint, part of the definition, or you just start with a particular return on spend?
So we are just assuming that the return on spend targets are 1 because you can divide through by the value. So you can like basically non-dimensionalize. So that kind of removes it from the particular form from the ODE. So if you just adjust the values, basically you can divide each value by the target. So okay. So what's happening as we kind of run this system is that M1's going higher, M2's going lower. As M1 gets high enough, then bidder 1 is bidding enough to start winning the second item. Once it wins the second item, it actually has a negative utility because it's far overpaying for that item, which means that it needs to drop its multiplier. So it starts to drop its multiplier, and then actually the system goes to a new equilibrium at 2-1, and this is bidder 1 wins item A, and they're both really essentially tying over item B. And so you can imagine that if I just swap this, M2 was high and 1 was low, there would be a symmetric equilibrium at 1, 2. So let's put this kind of all together in terms of the global dynamics. So here's really a plot of the vector field. M1 is along the x-axis, M2 is along the y-axis. What you're seeing is the vector field and the 3 equilibria that we found. The equilibrium in the middle is that equilibrium at 2, 2, where bidder 1 wins item A, bidder 2 wins item B. If you start on the diagonal, let's say anywhere else, let's say above 2, 2. If you're above 2, 2, then both bidders' utilities are negative. So they are going to drop their multipliers until they reach that equilibrium. If you're below 2, 2 at like 1.7, 1.7, they're really underpaying for their items. So their utilities are positive, they're going to keep increasing. But if you perturb off of this equilibrium, even just a little bit in any other direction, then you're going to fall into one of the 2 stable equilibria. And these 2 stable equilibria are the ones where one bidder wins the item that they valued highly, and they're tying on the other item. So even in this simple 2-bidder system, there's actually a rich global dynamics happening. There's a bistability. There's 2 stable equilibria and 1 unstable equilibrium. And one of the things that we show in the paper is that this kind of qualitative picture is really all that can happen for 2-bidder systems. So in 2-bidder systems, any trajectory, any bounded trajectory will always converge to an equilibrium. So basically the most complicated the qualitative picture of the dynamics in 2-bidder systems is that you have a bunch of equilibria and these connecting orbits between them. Okay, so what about for 3-bidder systems? So we characterize 2-bidder systems. What about for 3-bidder systems? Can 3-bidder systems oscillate, or do they always converge to equilibrium? They have more complex dynamics. So to understand this, we're going to kind of get some intuition from biology, and in fact, synthetic biology. And there's a very nice paper. It's really a seminal, groundbreaking paper in synthetic biology published in Science by Alowitz and Liebler. And what they did was they really built a synthetic genetic network. So a network of genes engaged in mutual repression, which exhibits an oscillation. They call this the repressolator. So what's the principle here? The principle is really kind of a rock, paper, scissors type of principle, an intransitive relationship. So if you imagine these genes as, let's say, being instead populations of animals or strategies, you have rock, paper, and scissors. Why would this oscillate? Well, let's imagine that rock population is high. Rock population is high, then its smashing all the scissors, scissors is gonna go low. Scissors is low. There's nothing really to cut paper. So paper can grow. Paper can grow and in turn cover rock. Once rock is covered, scissors is allowed to grow. So this intransitive relationship actually allows you to cook up an oscillation. Okay, how can we apply this to the bidding system? Well, we'll have 3 bidders, 3 items, and the repression effect is going to be through one bidder being a price setter for its neighbor. So we're going to try and construct what we call a bidding represslator. So every bidder has 2 items that it's interested in, a high value item, a low value item, and it's going to repress its neighbor through its low value item, through which it sets the price. Why would this, what's the intuition for why this might oscillate? Well, imagine that first bidder's multiplier is increasing. As it's increasing, it starts to put pricing pressure on the second bidder. That brings down the second bidder's utility. That utility becomes negative, its multiplier starts to come down. Its multiplier comes down, bidder 3's utility goes up because it's relieving pricing pressure there. Bidder 3's utility goes up, the multiplier can go up. That increases pricing pressure on bidder 1. Bidder 1's utility drops, its multiplier drops. That allows bidder 2's utility to come up. Okay. And when we run the system, that's basically exactly what we see. We see that there's an oscillation. And we can encode this repression effect as a graph. So in this case, we have the bidders or vertices. Any edge corresponds to an item. The item is valued by 2 bidders, and the direction of the edge is from low value to high value. The direction gives the rate of, or the relation of repression. So this is indeed a bidding represslator, which oscillates. How can we use this now to construct even more complicated dynamics? Well, one of the things that we can do is, now that we have this bidding represslator, let's just use it as a motif to construct higher dimensional systems. So we're going to couple this represslator by 3 represslators coupled together with 3 new items that link them together. And when we look at the time series of the multipliers, this is now much more complicated than just periodic orbit. This is what you might call quasi-periodic. So what is happening here? Well, it's a nice way to actually look at this is through what's called the phase space. So remember, this is a 9-dimensional system. If you're looking at a trajectory of the system, this is tracing out a curve in 9 dimensions. And as you're running the system, this curve gets longer and longer. What you can do is take your 9 dimensions, let's say project it down onto 2 dimensions, and that's these 2 plots. So these 2 plots are the projection onto 2 dimensions of the long-term trajectory, the entire trajectory of the system. First plot is a projection onto the first 2 bidders. The next is just a random 2-dimensional projection. What you're seeing is that there's actually a torus here. Why? Well, the system is so complex that it actually has multiple periods. These periods are incommensurate, meaning they have irrational ratio. So as the system is evolving, it never gets back to itself, and it ends up tracing out a formula in the phase space. Okay, and so that is how you build complex dynamics in auto-bidding systems. That's all I have, and I encourage you to check out our paper because there is a lot more in the paper itself. So thank you.